Right. Okay. Now, as you can see that I have got a carom board here. Okay. Right. Now you can see the striker. So one by one diagram. Let us see. Let's try to understand. See now here I am holding the striker, and my finger is here. You can see. Huh? So the finger is not yet touching the object at time t naught. Can you see t suffix naught? T naught. T naught means what is t naught? It's an instant of time. The object is not touching at t naught, and hence no force is available for the change. For this, no force is available for the change. Okay. Okay. The state of motion is at rest. So the state of motion of this striker is at rest. Do you appreciate that? Yes. Okay. At time t is equal to 0. So the velocity vector at time v bar of t is equal to 0 bar for t naught less than t1. So what is t1? What is t1? Louder. Correct. Tell.
The instant of time after t.
Excellent. Brilliant. So in the instant of time after t0. So less than t1, this I am not applying any force. So it is at rest. Okay. Now next this one. The finger is touching the object at time t is equal to 0 and moving forward steadily for time t1 to t2. Right? T1 to t2. Okay, I'll explain that. Force is available for change and the state of motion. The velocity of the object is steadily increasing, that is, it is accelerating as long as the finger is in contact. Vt is increasing from t1 to t2, hence non-uniform velocity. So now the instant of time is t0. Now look at the striker. Now my finger is here. Can you see my finger? Now my finger is now going to move. My finger is now going to move. Right? So my finger is moving. At time t1, my finger touches the striker. And then my finger continues to touch the striker till time t2. Of course, I showed it in slow motion. I mean, in reality, you see, my finger will touch. You see it? What happened? From t1 to t2, my finger was touching the striker in contact. So at that instant, for the time t1 to t2, force is being applied. And what did you observe during the time? The speed of the duster, the speed of the striker steadily increased till time t2. Okay. So therefore, hence the non-uniform velocity, right? So therefore, there was force acting between time t1 to t2, and the body's velocity during the time t1 to t2. What was the velocity of the body?
It was non-uniform.
Uniform, non-uniform. It was changing. Uniform means it will not change, both magnitude and direction. Here, direction was same, but magnitude was increasing. Right? So therefore, in that interval of time, it was accelerated. So the first instance is at between the time t0 to t1, my finger is not touching, no force is acting, the body was at rest between the time t0 to t1, and it continued to be in the rest between the time t0 to t1. T1 is the instant when my finger starts touching. So between time t0 to t1, no force is acting and the body continues to remain in the state of rest. This is in accordance with Newton's first law of motion. Second thing is, from t1 to t2, there is force applied, and therefore the body's velocity is uniformly changing, and therefore in accordance with Newton's second law of motion. Second law says the velocity of the body changes if and only if the force acts, and the amount of change is proportional to the amount of change of motion is directly proportional to the amount of force acting, and inversely proportional to the inertial mass of this. If I have taken a bigger body, then for the same force, the change would have been less. That is in accordance with Newton's second law. And now you see, again, see now observe all of you very carefully. So here, t0 to t1, no force is acting, it is at rest. From t1 to t2, the force acted. After t2, was my finger touching the striker? No, but the striker was in motion.
Yes.
So that you see here, again the finger is not touching the object from time t2 onwards. Hence, net force available to change the state of motion. There is no net force available for change of motion, but the state of motion is uniform velocity. After t0, you saw that the striker was moving with uniform velocity. That is again in accordance with Newton's first law. Okay? The finger is not touching the object after time t3, but the frictional force is available. See now here. See now here you see this experiment. So after t2, its velocity from t1 to t2, its velocity increased. Then its velocity decreased by itself. My finger was not doing. Why did it decrease? Because there was an opposing force called as frictional force acting. So frictional force becomes an external force or the net force, and that is the consequence of the change of motion. That is again in accordance with Newton's second law of motion. So now I think all of you have experienced Newton's first law and second law. In practice, in practical. Is that clear to all of you? Hello? Right. Any questions? So carom board is the best way to understand Newton's first law and second law. And you can apply it now to all the objects that are in motion. But with a speed very much less than that of the light, and the body's size is quite big, not very small like atom. Okay, so now this is interesting. For a particle in accordance with Newton's first law, change in the linear velocity. Now I am using the word linear velocity because you are soon going to see that force will also cause rotational acceleration, change in the rotational motion. So I want to differentiate between the two. So I am using the word linear velocity.
So, but you have said that it is a particle.
Yes, wait a minute. Now, when I am doing this experiment, you should consider that this striker is a particle. Understood? That is an important consideration to be considered. Otherwise, also you see, my force line of action was what? It was passing through the center of mass, and therefore no there is no rotation. Right? Now you observe. I am going to do like this. Observe. Can you observe now? See, now I am going. See, my force is now not acting along the line of motion. What happened? Did you see it rotating? Hello? One second.
Yes, sir.
You saw it rotating and also translating. So, but if you do it like this, then the line of action is passing to the center of mass, then you will see only translated motion or linear motion. Okay? Now, for a particle in accordance with Newton's first law, the change in the linear velocity is only on account of net external force. Consequently, in accordance with Newton's second law, linear acceleration is directly proportional to the external net force and inversely proportional to the
Body's
inertial mass. So if I had taken a bigger striker, then for the same force, it would have moved, the acceleration would have been less. So therefore, acceleration is equal to, by second law, acceleration is equal to instantaneous acceleration is equal to instantaneous force divided by the mass. F bar T by M, where F bar T is the net force and M is the inertial mass. Correct? See, I am again using the word inertial mass. So there are other types of masses. The body is accelerated the instant of the force acts on it. However, significant change in the velocity occurs only after finite delay depending upon the inertial mass M. I suppose this is clear. Net force causes net acceleration or simply acceleration. That's
Sir, delay depending on the inertial mass means that if the mass is more, then the time taken for the velocity to change is also more.
See, now let us do it like this. Go step by step. If the mass is more, the acceleration is less for the same time. There ends the matter. Now coming to the significant change in the velocity. Okay, so there you see, yes, when you are talking about this, there you will see that if the mass is large, then you will see very insignificant change in the velocity. If the mass was less, you would have seen significant change in the velocity in the same interval of time. So supposing after you have tried the striker, you have chosen an interval of time, say 0.001 second. So if the mass is small, then in the time interval 0.001 second, you will see significant change if the mass is less. If the mass is more, in the same time 0.001 second, you will see less significant change in the velocity. So that is how you have to interpret. Now don't see, take one by one concept. Force, mass. Force upon mass, acceleration. Yes, the body's velocity has changed. Now significant change in the velocity. If you want to take into that concept, then there you see for the same time interval, now you consider another experiment. Now you experiment with the time interval. So for the same interval of time, when the force is applied, you will see large change if the mass is less, and if the mass is more, you will see small change in the velocity or significant change in the velocity. See, all this is happening in infinitesimal interval of time, delta t. See, that has only got to be perceived. You cannot experiment and show that. The delta t is so small, it is almost equal to 0 but not equal to 0. Our eyes and sensory organs are not so sensitive to notice change of the order of 0.001 second. But you have to understand it notionally that this is precisely what happens. Because what is important here is, supposing there is a ball hanging, the big body hanging, and you snap the thread, and if you capture it on a camera, you will see the thread getting cut, and you will see the body actually starts moving. So you will see that there is a time between them, 0.001 second. So that delay is something that you have to take into account, okay, in this, for all these cases. That is precisely what is it. Okay? Acceleration is in the same direction of the force, irrespective of the direction of the acceleration vector is in the same direction of the force, irrespective of the direction of the velocity vector. Now try to understand this. Try to understand this concept. Okay? So here you see, this is the body. At some instant of time, its velocity vector is this. Its velocity vector is like this. And then you are applying at that time t a force vector f1. Right? As soon as the force vector acts, then consequently what I have to attach to this?
An acceleration.
Yes, an acceleration vector. So I will attach the acceleration vector instantly like this. At time t, force has acted. At that time t, you will have acceleration vector. Irrespective of the direction of the velocity vector, the acceleration vector comes into play.
So, but the resultant of
wait. See, everything is happening at the instant of time. This acts, then this comes into picture. At that time, this was like this. At time t. Now, at time t, the force has acted, and there is acceleration vector. And at time t plus delta t, delta t is very small. The acceleration vector is almost same. The force vector has not changed. Small interval of time. But then you will see that this velocity vector, which was like this, now would have become something like this. This is at what? Time v t plus delta. Understood?
yes.
Instantly it did not happen. At delta t, this happened. But during the delta t, neither force has changed nor acceleration has changed. Acceleration vector has come into picture at time t. But the velocity vector changed significantly after time delta t. This is the picture. Got it?
Yes, sir, but according to the second diagram, sir, force is also acting on the time t plus delta t.
That is what I am trying to tell. The delta t is so small, for all practical purpose, it is 0. See, that is what you have to understand. This force vector did not change. Acceleration vector did not change. But the velocity vector changed. So when you want to perceive the velocity vector, delta t becomes insignificant. But when you want to perceive the force vector and acceleration vector, delta t is insignificant. So this is where, things become difficult for the teacher and student. Okay, so that is why, these things are seldom taught. But unless you understand this, you will not be able to attempt the difficult questions in examination. Okay, so what is simple is, the response. What is the response? Change in the velocity is the response. So the response cannot happen in 0 in the time. The response will happen in finite time. That is what I want to tell. It will not happen instantaneously. It will take very small amount of time, but not equal to 0. That is the perception that all of you should know. There is something called as response time, response to stimuli. Stimuli and response. There is always a time. It cannot happen instantaneously. If it has to happen instantaneously, then the mass must be 0. As long and if more the mass, more the delay in time. That is what you have to understand. Correct? Right. It must be noted that if a body A experiences force Fa bar, then it must be there must be at least one more body which interacts with body A to produce force Fa. Understand? See, now I am pushing the striker, or the striker's motion has changed. That means force is acting on the striker. But where did this force come from? Okay, in this case I am pushing. In the case of moon and earth, the gravity of the earth is holding the moon. Understood, all of you? So there are different forces. So here will not talk about different forces. What we will only say is, if one body is experiencing force, then there must be another body to apply force. The same body cannot apply force on itself. Understand? I am able to walk because I am kicking the earth and earth is kicking me. If there is no earth beneath me, imagine you are in the hawa, then you cannot walk. If somebody lifts you with your shoulders and your feet is hanging, then it will be hanging only, you cannot walk. You will not move forward. Understood? So the idea here is, you observe, if body A experiences force Fa bar, then there must be another body B which is responsible for Fa. Okay, now see. Then there must be at least one more body B which interacts with body A to produce Fa bar, and this you can call it as action. It is interesting to know that body A in turn also interacts with another body B to produce force B and called reaction. So body A experiences force because of body B. But look at the nature. If body B is applying force on body A, that means it is interacting with A, then automatically body A will also interact with body B. So if this is applying force, body B is applying force on A, then A will automatically apply force on B. Now you see here, automatically in the word, here in this word, I am considering bodies which are not living. You understand the definition of body there? It is just collection of particles. See, now please understand. So here you see there is body B applying force on A, if you call it as action. Body A applying force on B, you call it as reaction. And Newton proved it that Fa bar will be equal to minus Fv bar. That means action is equal and opposite to reaction. This is provided both the bodies are interacting. This is provided both the bodies are interacting. That is important. Okay. Now there are situations. A dog bites you. Action. Reaction. You bite the dog. It doesn't happen. Right? Now in physics, this is a live example. This is example with a living being. But in non-living things also, you will see some interesting things like this. Okay? You will soon learn that. So therefore, you should be cautious. See, now supposing I have a conductor carrying current I1. And there is another conductor carrying current I2.